Buenas tardes.
Good afternoon, good evening. It is for us great pleasure to introduce Professor Reinhard Genzel, who's going to make a lecture, part of his cycle. He is a director of Max Planck Institute, Extraterrestrial Physics from Munich, and he is also a professor from Berkeley, California University, full professor also at Munich University. He's going to talk about massive black holes and the evolution of galaxies. This relationship that's been established in the case of our galaxy, thanks to his contributions, go beyond that, and that goes on to other galaxies. That's a hint. Massive black holes and galaxies and the process of formation, they go in a parallel mode along the cosmic history and evolution. In 3 minutes, it's impossible to describe the very many contributions made by Professor Genzel, but as part of the great impact of his contributions, we can see the long list of awards he's received, and I'd like to mention some of the notable awards. We can mention the Crawford Prize back in 2012. It's like the Nobel Prize of Astronomy. He got the award in 2012 with Professor Gert from University of California, Los Angeles, and it was a token of recognition to the study made by Professor Reinhard Genzel of the movement of stars and the core of galaxies. At the central part, there is a supermassive black hole with a mass that's 4 million times the solar mass. It's like a monster in lethargy there because of a low accretion rate, as we will see during the presentations. But the monster, so to speak, is there. Professor Genzel and his team, they had contributed to knowing the evolution of galaxies, studying infrared wavelengths till millimetric and submillimetric wavelengths, and observations with instruments and telescopes like a very large telescope and others like NOEMA and ALMA, the interferometers. They had studied the content and the dynamics of gases in different populations, different from galaxies, at different evolution state, different red shifts at different moments of the history of the universe. Professor Reinhard Genzel and his group, they had fostered the development of lots of instruments, lots of different telescopes, and most of the data we will see were obtained by the Very Large Telescope, and his group was in charge of constructing symphony device, which is key. Also, millimetric interferometry and other tools, the Millimetric Astronomy Institute with the contribution of Germany, France and Spain. It's a teamwork trying to get the best possible space resolution for wavelengths, allowing us to study in detail the core, the nucleus of different galaxies. In this effort, in this constant effort, Professor Genzel and his group, they had started now studying the gravity instrument, which is an instrument that with the VLTE interferometer will allow them to reach regions that are close to the black hole. In the middle of our galaxies, we're talking about radios close to the horizon. In the case of the black hole, in search of this black hole, this event horizon in this hypothesis confirmed that there is a massive black hole in the central part of our galaxy. That means that Professor Genzel's contributions are very promising regarding results. As Reinhard says, success, and in the case of a scientific project, resides in our commitment the technical people, scientists working together as teamwork in search for excellence towards the main goals of a project. You would realize there are very many contributions, and he is part of the elite of scientists whose contributions will have the greatest impact on contemporary astronomy. We have to say that when a person knows that Reinhard has published an article, a paper, immediately this astronomer knows it's a must to read, because this article, this paper, published by Professor Reinhard Genzel will become a reference. It is a reference. And without further delay, we're all wanting to enjoy the wonderful lecture by Professor Reinhard Genzel. So the floor is to Professor Genzel.
Thank you, Santi. Thank you very much for these very kind words, which I blush because, one doesn't get to hear good things often. Now, first of all, I would like to welcome you, ladies and gentlemen, on this occasion. And I hope I can give you a story of modern exploration, which has taken basically 100 years, you will see why, which has come to a certain culmination now. And that's a story about the subject of black holes, which I'm sure you're all experts on. Probably more than me. And it's always a wonderful thing that the public at large participates in the research endeavor. It's not only a wonderful thing, it's essential. It's one of the very important things of the modern era, that we understand that research, exploration, curiosity, progress in science, but also progress in technology following from that, and the well-being of our countries are strongly coupled. The building up of a research endeavor creates elite places like universities. In those elite places, you have young people getting excited about the future, study up, help in the research, perhaps stay in the research, but maybe also wander on, move on to industry and develop technologies which then help the country as a whole. So it's so important that this story of modern science is maintained, and it's maintained by you people. You are the ones who, in the end, of course, give us the funding and support us, and if that is not there, we won't be there. So black holes, of course, is a subject of public interest for many reasons, because sometimes people believe you could use them for travel, for instance, space travel, or to remove your debt in the case of the financial circles, etc. And there are many reasons why they are fascinating in this sort of general respect, science fiction and so forth. However, black holes also have, as we now know, a very important role to play in the universe. And that's really part of the story which I would like to tell you about. And it all started 100 years ago. Really, truly 100 years ago, almost to the day. And that is, of course, the publication and the first solutions of the general theory of Einstein's theory on relativity. Einstein had been working on relativity for a long period of time. The initial theory, called special relativity, dealt with the fact that what happens if objects move at very fast speeds. Now, we knew from experiments, and Einstein knew from experiments, that there is a maximum speed limit in the universe. That's called the speed of light. And it was verified experimentally, and that is at least temporary truth for science, experimentally, that nothing can exceed that speed. So while we know when we both sit on race cars and you travel twice as fast as I am, that I can see you moving at twice the speed if we are in normal race cars. But if I and you travel on race cars which travel fast at the speed of light, then this exercise becomes a little more difficult, because we cannot exchange communication at faster than the speed of light. So that was a special theory. In the general theory, Einstein tried to connect all of this to the geometry of space-time. And he was able to formulate the actions of masses and energies in the universe as a geometrical principle where objects, masses, distort space-time, and other masses then have to follow action in this curved space-time. So the planets move around the sun, so to speak, because the sun created a dent in space-time, and the planets cannot anymore go on straight lines because the space-time now has a dimple in it, and you have to basically move in circles, and that's the orbits of Kepler and Newton. Now, one of the consequences of this theory was, if you connect it to the special relativity and the whole issue of speed of light, is that there are objects which come out of this theory, which in a way is fairly natural, that we now call black holes. So what are black holes? These are really mass concentrations to start with. Any mass concentration would do. Now, gravitation, as we know it, of course, on the Earth, is something which has to do with our mass. So the gravitational force and the gravitational energy and so forth is proportional to the mass of the object. But there's a second element, and that's the size or the distance. So if we would make the Earth smaller, and we would live on the Earth of that radius, we would experience a higher gravitational force. And there is, if you think of a sun or an Earth where you send a rocket into outer space, a maximum speed which you have to give that rocket in order to escape from the surface of the sun. Now, in the case of our Earth, that's some 30,000 kilometers per hour. But if you make the Earth in your mind an object of the size of 1 centimeter, or you make the sun in your mind an object of 3 kilometers, then the Newton's theory or Einstein's theory tells you that the speed of that rocket now has to be the speed of light. So that means if you make the object still a little smaller or the mass a little bigger, then no light can escape anymore from that object. And so that's the principle of a black hole. And this surface within which then light cannot escape, we call the event horizon. And that's a very profound principle, because if you go through the theory, Einstein's theory, there is indeed a separation of worlds. If you take your rocket and you fly into a black hole, if you're sturdy and you fly straight through the black hole's event horizon, you yourself shouldn't really, in theory, not notice much. That's the result of general relativity. But you are now destined for death, because in a finite time in your reference frame, you'll end up like any other object which has made the same trip in the center of this body called black hole, where you got collected with all the other debris in a central singularity, which then, by mathematical construct, has infinite density and is called a singularity. So that's bad news. On that trip, once you pass through the event horizon, you cannot go back and send messages out to your friends back home. Why? Well, because any message you would send out is the speed of light, and that won't be able to climb back out of the black hole. So there is a separation of communication at the event horizon, and the black holes cloak themselves with this mysterious barrier. But the real very strange thing of general relativity, of course, is the prediction of this singularity. Now, we believe nowadays that this is probably wrong. It's probably wrong because the theory is as we call it, a classical theory. It does not take into account quantum fluctuations and the Heisenberg principle and so forth. So once you take that into account, most every physicist on Earth is fairly sure that that will soften out the central singularity into an object which has a certain size called the Planck length, which is incredibly small, but not zero anymore. And so the infinite density probably in that sense is a reflection only of the theory which is not correct in this limit. But for the practical purposes of this talk, think of black holes as big concentrations of mass, and if they're massive enough and small enough, then they cloak themselves behind this communication barrier called event horizon. So Albert Einstein's theory in principle was presented in November 15 and then published in early 16. And the first solution of a spherical mass with the property of of black holes was then published only a few months later by Carl Schwarzschild, who unfortunately died. It's remarkable that he published this paper sitting at the frontier on the Russian front. And he died of a disease a few months later. What a terrible thing these wars do to us human beings. Now then it took 50 years, 60 years for further progress. The next one is to recognize that not only mass, but then also the rotation, spin of a black hole can play a role. And finally, electrical charge as well, although that does not play much of a role for astrophysical objects. So black holes for general relativity are very simple objects. You only need to know two things, mass and spin. You don't have to have any prescription of valleys and mountains on the surface, or whether they are round or spheroidal or any other shape. No, only two numbers are sufficient to describe them. That's fantastic how simple these objects are. Now, they are more complicated when you go to the quantum theory, which I have to say we don't have yet. But one quantum property of black holes is very plausible for any physicist, and that's the application of the Heisenberg uncertainty principle at the surface, right there at the event horizon. Now, I told you the event horizon is a fictitious barrier of communication. There's nothing hard there. You can fly through there, but nothing can come out of it. And there comes the uncertainty principle in form of Hawking's radiation, that at that surface you can manage or you can think of a process, a quantum process, where just at the surface, one photon is created going in one direction, another photon in the other, or a particle going one in the direction, the anti-particle going in the other direction. And the one particle which goes out we can see, and the other one we cannot. And so this property, which you can calculate on the basics of very fundamental physical principles called thermodynamics, you can compute, and should be a property of black holes. Can we ever measure it? Probably not for the big black holes I will talk about. Maybe for other black holes, which we might see in the future. But for the species which you will hear about in this lecture, Hawking's radiation is so weak we won't be able to see it. So we are stuck with two numbers, mass and spin, to describe these black holes. So that's the theory. Theories are, in physics, chemistry, and other sciences, useless unless you can validate or contradict them by experiments. So we would like to, of course, now take experiments and look for these objects. So let me tell you the story about that one. So I mentioned the black hole event horizon, and that story really is one which I would like to introduce with taking a trip from our position in the Milky Way outside. So what you're seeing here is a trip which we are taking in a fairly realistic setting of the environment of our Milky Way, starting from the Milky Way. And every object you see on here really does exist in reality. And these objects you're seeing are called galaxies. They're sort of the island universes where we, form of stars, gas, and us humans live. And a typical Milky Way, like you see in here, like our own, which we started with, and then the others in our vicinity, have typically up to 100 billion stars. 100 billion stars are in every one of these Milky Way systems. And of course, the astronomy community has been researching our extragalactic environment, these Milky Way systems, and try to understand what has created them. How have they formed? When was it? What processes were involved? And when has that all taken place? So I'll tell you a little bit about this today. But in the context of the black holes, I will tell you that every one of the objects you see in this movie here, probably every one of them has a central massive black hole sitting, which is about 1/3 to 0.5% of the mass of the entire system. So the story, that's the story of astronomy, is that black holes indeed are present. And I will tell you also what their role has been probably in the evolution of these Milky Way systems. So this part of the story really also started in the 1960s, 50 years ago, with the discovery of the so-called quasars. At that time, radio astronomers in the United Kingdom as well as in Australia started with their new radio telescopes, mapping out the sky at radio wavelengths and finding new objects. And sometimes they would find objects which on modern pictures in the optical look like stars, but in the radio wave bands are very powerful. Therefore, the name quasi-stellar objects, quasars. So here's a quasar in a modern Hubble Space Telescope picture, where you see that there is a very bright central region of what otherwise looks like a massive but normal galaxy here. And this bright central region, that's the quasar. That's where the radio emission comes from, typically very time variable. Sometimes you see very collimated jets of radio emission emerging from these objects. But surrounding this is a fairly regular, in this case, spiral galaxy, massive but otherwise regular. And that's the rule for these so-called massive objects, quasars and other what we call active galactic nuclei. And when they were discovered, of course, immediately the question arose, how could you produce the energy for these quasars? We know that galaxies are powered by the fusion, essentially, of hydrogen to helium in the stars. So could it be that quasars are just central, very dense concentrations of stars, which are very bright because there are so many stars there? Now that was investigated immediately by the theorists at the time, and we know that fusion is a very efficient process of generating energy. About 0.5% of mc squared can be converted to radiation and other forms of energy. But for the purposes of these quasars, that's not sufficient, actually by far not sufficient, to power quasars for any length of time. So the conclusion was you needed something which is far more efficient there. And that then, within 10 years, led to the theory of accreting what we now would call black holes. Back then, it was not called black holes. That term was coined a few years later. They were called Schwarzschild throats. Okay? So the idea here is that when matter falls onto a black hole, that the black holeness, that is, the non-visibility, only happens, of course, when the material disappears behind the event horizon. But before, outside of this event horizon, the infalling material can convert its gravitational energy into heat and radiation. And it can do so very efficiently exactly because the speed of material in the vicinity of the event horizon is so fast. It's a fraction of the speed of light, half speed of light, 0.6 times speed of light. And if you can convert this into an energy efficiency, what you find that it is 10% mc squared for a non-rotating black hole, and up to 40% mc squared for a maximum rotating Kerr Schwarzschild black hole. So that's pretty impressive. In principle, while black holes are black, because material, so to speak, once it enters the horizon, cannot communicate with that outside of the event horizon, the conversion of gravitational energy into radiation can be so efficient that it outshines fusion by 2 orders of magnitude, a factor of 100. So that has become the standard model of trying to explain quasars. A standard model which is sufficiently good to explain many of the light phenomena, for instance, the radio jets which I mentioned, for instance, very hard radiation in X-rays or even gamma rays. Very fast time variability of the radiation, which tells you that the volume from which the energy is generated is very small. So this black hole accretion model has been the standard model for explaining quasars, but is it true? And what would we have to do to prove that it is true? Well, after all, a black hole, I told you initially, is a concentration of matter. And Lindenbell and Rees, in a very influential paper in 1971, basically said, suppose every galaxy has a central black hole, like these distant quasars. Well, then we should be able to see the influence by gravitation onto other bodies, onto the environment of that central black hole. And Lindenbell and Rees came and basically constructed a number of recipes what the observers should do. And in reality, it's really rather simple. An unambiguous proof of the existence of a black hole obviously is you should measure the gravitational potential. Gravitational potential down to the scale of the event horizon. Inside of that, you won't be able to do this, but to the scale of the event horizon and show that basically, it's so concentrated that all the energy and mass is inside of that. And how do we do this? Well, think of the solar system. Okay, here's the sun and the planets. We know from Tycho Brahe's measurements and Kepler's analysis that the planets move on almost circular orbits. And since they're bound to the sun, and this is much more massive than the planets, they are orbiting the sun with a speed, an orbital speed, which goes like 1 over the square root of r. That's the basics of Kepler's laws. Now, that same result you'll get in Newton's theory, and the same result you also get in Einstein's theory if you have basically orbiting particles around a massive object. Well, now, suppose you had Einstein's or Newton's or Kepler's theories and Tycho Brahe's data at the time, but the sun wouldn't shine. What would you as a scientist have to conclude? You would have to conclude that there is an object of 1 solar mass at the center of the planetary system, geometric center of the planetary system, very concentrated in size. From the orbit of Mercury, we could even get some ideas that it is not exactly a point source, but still, you would basically say it's very concentrated mass, which outweighs the other planets by a factor of 100. So you don't need to see the object. You see it through gravity. Okay, so that's the idea, and that's what we and others are doing to hunt for black holes elsewhere. Now, that said, paper of Lindenbell and Rees made another observation, which is for astronomers very obvious. Quasars, the ones where this idea came in first, are very, very far away. The nearest quasars are typically 1 billion light years away, 1 billion light years. So that's, a significant fraction of the travel time of photons during the time of the universe. So quasars are very far away, and therefore, if you want to see objects in the centers of quasars orbiting something, that's a hopeless endeavor because of the measurement techniques would require you to measure to angular precisions which we just do not have and won't have for some time to come. So you have to be happy to verify this principle not on quasars, but on objects which are closer, hoping that they have the same central massive black holes as the quasars might, according to that hypothesis. And so that's the idea of Lyndon Bell and Rees. Go and measure the nearest galaxies, extragalactic systems, and the nearest of all is our Milky Way. Our Milky Way is 100,000 times closer than the next quasar, and it's only in astronomical terms 25,000 light years from us. So there is a chance, and as you will see, that has borne out, to actually make empirical measurements of the type which I've sketched for you, Kepler experiment, and prove that there is a central object which, as you will see, we now think shows that there is a massive black hole beyond any reasonable doubt, as long as general relativity holds. So I'll tell you how this was done. So it really, for us, has been a story of endurance, endeavor, exploration, and hard work with young people in southern Chile, with the European Southern Observatory, ESO, which Spain is part of, and the machine which you see there on Paranal Mountain with 4 8-meter class telescopes. This is really the premier optical near-infrared observatory in the world now, with these 4 telescopes, plus other telescopes which you see on the mountain as well, which I won't explain in detail. And the story really has been one of basically trying to measure with high precision the positions of stars near the Galactic Center, to measure then the motions of these stars by doing the measurement over and over and over again over the years, and hope that if there's a black hole, well, then the stars would move, very much like the planets in the solar system. So that's the Kepler experiment. In the second set of improvements, we needed to exclude the effect of the Earth's atmosphere on the images. As you well know, if you travel with a car on a hot summer here in Madrid, I'm sure, outside between Madrid and Toledo, for instance, and you look at distant stars, well, then the image of that star is flickering, it's flimmering, and that's because of the refraction of the Earth's atmosphere. And the refraction of the Earth's atmosphere is our enemy to make sharp images. Doesn't matter whether you have a 20-centimeter telescope or an 8-meter telescope. So that we had to improve, and that's called adaptive optics. What we do, we basically analyze the waves coming from the star or distant stars, and then correct for the actions of the Earth's atmosphere. This has to be done with very efficient optomechanics, and as you see there, also so-called laser systems, which we use as artificial beacons to make the measurement. So this phase has then equipped VLT, but also the Keck telescope in Hawaii with telescopes which can look as sharp as 8-meter class telescopes can do in the near infrared. And that's much better than what Hubble can do. So Hubble is very greatly important, but it's a small telescope. Now finally, the last step which we have undertaken in the last 10 years in terms of development and have now brought to the mountain is what you call there at the bottom and see, it's called gravity. That actually is now coming to fruition this year, where we've combined the light from all the telescopes here, from this telescope, that one, in a central station here. Now, as I told you, every one of these guys is 8 meters in diameter. Now, the separation between that telescope and that one is 130 meters. So if you interfere the light between these telescopes, you're basically generating the resolution of a telescope which is 130 meters in size. We will never build such a telescope, but we can basically create it through experiments by interference. And so that's how we want to get still higher resolution. In fact, so high that come next year when we start measuring in earnest, we should be able, in principle, to resolve, and I am careful to say this, the event horizon of the black hole. Because the event horizon of the black hole in the galactic center, as you will see, is 10 micro-arc seconds. That's a euro cent coin on the moon. So our instrument actually allows you to see the difference between the left side and the right side of a euro cent coin. Good that we made them that size on the moon. Okay? So that's the kind of thing you need to do. And for the young people amongst you, science is really an endeavor of exploration and of patience. All of this, now that we are 25 years into the game, took a lot of work by the young people and also basically courage, and basically also not listening to people who will tell you this will not work. You have to trust your own intuitions, and you have to go forward, work very hard, and sometimes you're lucky, not always. And so I've had the extreme pleasure to have been working with young scientists over the years. Here you see our current team. In fact, I should point out this man here, Frank Eisenhower, who has been the principal scientist of both this instrument, Symphony, and this one here, Gravity, our most recent one. So it's really, science is a thing where young people get to really do frontier work in research. So what have we found? I show you here a picture of the central part of the Milky Way. We're now on a scale of about 1 light year, and the colors you see are not colors in the optical. Why not? Well, because when you look at the galactic center, there's a lot of soot, dust between us and the Milky Way center, which we call interstellar material. That's the material from which new stars form in the Milky Way. For the purposes of looking at the galactic center, however, they dim optical light by a factor of 10 to the minus 12. So it makes it essentially impossible to look in the optical, although that's what we would like to do if we could. So we basically move a little bit out of this soot band, if you like, to longer wavelengths in the infrared, 2 micrometer wavelengths, about 4 times wavelengths of visible light. And so there, with the big telescopes, we can make pictures like this in 3 different bands. So the colors indeed are infrared colors. What you see are many stars. The density of stars here is about 1 million times higher than in the solar neighborhood. So if you live on one of the planets there, which I'm sure exist, well, you wouldn't see much night there. It's all daylight all the time. Now, I should say that what you see here is not stars like the sun. None of these objects here are solar-like stars. And that is extremely surprising. Why? Well, because stars live only a certain period of time, and their lifetime depends very strongly on their mass. So solar-type stars, which are very common, live very long, but they're not very bright. They would not be seen here easily on these images. More massive stars live very shortly. And some of the stars which you see here, the blue ones, this one for instance here and here and here, they're all only a few million years old. We can check that out through spectroscopy and other techniques very well. A few million years. And so they must have formed there, we think. But that's very difficult to do in the environment of a black hole, because the formation of stars, we know in the Milky Way, occurs from thin interstellar clouds, where the hydrogen density is, 1 hydrogen density every few cubic centimeters, and or maybe a few 100,000 times bigger. So this is very thin gas, which then over time collapses under its own gravity to form a new star. But that cannot work in the vicinity of a big black hole. So when these stars were formed, actually, everyone felt, okay, well, there can't be a black hole there. The theorists, in particular Lord Rees, who had been proposing, look here for a black hole, said, oh, well, there won't be a black hole. Well, now that we know that there's a black hole, of course, that begs the question, how come that there are these big stars? And that's a very fascinating story in its own right, but I don't have time to go into it. For the purposes of this discussion, it's tremendous luck. Nature has given us very bright objects, which we can see with our techniques, and measure the gravitational potential. That's all we care for this talk here. All right, so what have we found? So you see here a circle. This cross here is the position where there is a very compact radio source, which had been found about 30 years ago, Sag A star called, which was already known then to be very compact and might be, so to speak, the location of the possible black hole. And so within a light month of this black hole, we now look at the motions of stars and ask ourselves the question whether there is a central mass concentration. So here's that light month. And then what I show you in 3 different colors, red, green, and blue, are the images with the VLT in 3 different years. Year number 1, year number 2, and year number 3. So it's obvious that this star here, quite close to Sag A star, moves very strongly. You can separate the images from different years very nicely. And that means, when you look up here, that its motion is about 3,000 kilometers per second at that time. Now that's 100 times faster than the Earth around the sun. Now, if you use the simple Newtonian gravity, you immediately, from this notion, can calculate in about 10 seconds in a calculator that there must be a mass there, close to this, of a few million solar masses. Okay? Just because the object, the star there, moves so fast. Must that mass be concentrated? Well, we think back to the Kepler experiment I mentioned to you, where I said the characteristic of a concentrated mass, which you cannot see, is that the orbits which move around it move the faster the closer you come to it. Is that the case? Well, let's look. The closest object is obviously this, which has clearly a high velocity. Here, this one is faint, but it also moves fast. This one moves fast. This one a little less so. This one less so. Now go out here. You see now the prism effect, the blue, green, red effect becomes very small. And further out, practically not to be seen anymore. So that's Kepler's laws in a qualitative fashion for you. So you can make that quantitatively, and that's done here. You can plot the average speed of stars as a function of separated distance from the radio source here in the center. And there, that curve you see here is indeed a Kepler curve, 1/√r, around a few million solar mass central object. So that we knew in the mid-90s. Now, another principle of science, which is holy and is essential, is thou shalt not believe anything until somebody else has repeated the measurement and verified it's true. That's why the scientific community can catch aberrant traitors to the business fairly quickly. If the experiment cannot be validated and cannot be repeated, it cannot be true and is severely, at least, suspected and doubted by the community. In this case, a second group competing with us started working a few years after us at the Keck telescopes in Hawaii, Andrea Guess and collaborators at the University of California, Los Angeles, and they, a few years after us, came up with the same result, virtually identical results. So that gave a lot of trust in the experiment right there for everyone else to watch. So there must be an object, a few million solar masses, concentrated. But how concentrated? Must it be a black hole? Must it be a black hole? And the answer is no. Why not? Well, I mean, we have a volume here into which you can put this object, which is about this big, which is sort of a light weak. light week. That's pretty compact, but you could stuff, in principle, into this central region, at least hypothetically, 1 million neutron stars, or a few million white dwarfs. They wouldn't radiate much infrared energy, so you wouldn't see them in terms of the light they're producing, but they could make up the mass. So how about that? Could it not be that what we are looking here is an object which is really a conglomerate of objects which we already know, stars, faint stars, neutron stars, perhaps the other species of black holes we know to exist, so-called stellar black holes? And the answer is, in principle, yes. But such states do not live very long. And I'll explain that to you a little more next. They don't live very long because the interaction between the different stars in this conglomerate makes, in the end, this object to basically lose some mass to the outside and the rest collapses, and in fact forms a more concentrated, probably black hole type state. But it's a possibility. So the question then in the end 90s was, how can we come to a more certain conclusion? And the answer, obviously, is you have to make better measurements. You have to go closer to the central object so that you can eliminate any other option. And in particular, you must somehow find a way to measure more than just velocities. Because you see, to measure a mass, to know what mass there is from the motion of stars, you really need to measure 6 parameters. You need to measure 3 velocities, in the sky, as well as along the z-coordinate, along the line of sight. That we can do. The z-coordinate, which I have not discussed, we do through Doppler spectroscopic shifts of the stellar spectra. Then you have to measure 3 coordinates. On the sky, 2 coordinates, that we can do. But you have one more coordinate you need to know to have a unique solution of the problem, and that's the z-coordinate along the line of sight. You cannot get that from these measurements. So how do you get out of this? And you can get out of it if you measure more than velocities, because in the end, these stars are on some sort of orbits around the central object, like the planets around the sun. So what about measuring orbits, or at least elements of orbits? Well, we tested that through computers and made some modeling, and it turned out that the orbital timescales were hundreds of years. That exceeds the patience and the lifetimes of most researchers or research communities. So I think we were sort of stuck. But then nature was very merciful to us. It gave us stars which are on short enough period orbits that we can actually do it within a researcher's lifetime. And let me show you the best one we have right now. That's this object here. What you see here is the orbit of the star over time. Here we started up here in 1992. You see the time clicking away. There it was in 2001. The blue points are our measurements. The red points are those of our colleagues in California, so that gives you immediately a feeling whether these measurements agree or not. The radio source, the candidate central black hole, is down here, Sagittarius star. And so initially we saw the star basically moving down with a few hundred kilometers per second, then 1,000 kilometers per second. But then in 2002, all of a sudden it was on the other side of the radio source. I tell you, this was a momentous time when you really feel that your research career has worked out. You don't need any computer. In fact, I'd used a graph sheet to plot the points, and I actually fitted a sort of a Kepler ellipse to this by hand, and you get a pretty good answer. And a remarkable thing was that at that time, these points here stem from that time. This is not from year to year like you see here. This is 2001, 2000, and so forth. Here is month to month. The star was moving at a speed of 5,000 to 8,000 kilometers per second. And obviously now that you see the orbit, at that time was only about 17 light hours away from the black hole. 17 light hours is about 3 times the orbital radius of the planet Neptune around the sun. So we're talking about, planetary solar system scales, but at speeds of, several hundred times the speed. And so again, you can use Newton's equations and calculate the mass, which is enclosed. And what you find is the same mass we had seen before, now only within 17 light hours. And that really excludes essentially all other options, because now the volume you have left for anything to squeeze in there is so extremely small. Now this particular star we've followed since, and so we were getting better, and so did our UCLA colleagues in measuring. So here you see it's moving back out. Error bars are much better now. Here there's next year, and then we went through. And now it's coming back for the second time. There's 2016 from this year, and in summer 2018 it's going to be here again. So now we know what we're going to see, and now we want to do something new, which is we want to see the deviation from this best-fitting Kepler ellipse, which is in front of you, because the data are perfectly fit by a highly elliptical Newtonian Kepler orbit around a mass of 4 million solar masses, with a peri approach of 17 light hours and 16-year orbital period. So here, when it comes so close in summer 2018, so that's 2 years from now, we wish to use this opportunity to measure the deviations we have to expect from general relativity. And general relativity predicts a very strong deviation, strong in relative terms, I should say, which is a little shift of the orbit as the star moves around it. The Kepler ellipse in general relativity is not closed anymore, but it starts to precess a little bit. That precession over the orbit is 12 arc minutes. You couldn't see it on that scale, but we will try to measure it with this new machine called gravity. And we think we can do it over the next 4 years. And that would be the first time general relativity has been tested on these kinds of enormous masses and scales. So that's the story in the Galactic Center. Over the years, we've created with good scientific evidence from several measurements, evidence which shows that there must be an object in the center whose properties are consistent with a black hole, and it must be a black hole beyond any reasonable doubt, since we can exclude other options. Now, science is not only exciting, sometimes it's even beautiful. The question, of course, is where is the black swan in this? Okay. So we are measuring not just one star, but currently we have orbits for 50 stars. And so we can use this precision gravitometer to measure the mass very, very precisely. Our most recent measurements, we are just getting out of supercomputers, measure the mass of the black hole to about 1% accuracy, and the distance to the Galactic Center to 1% accuracy. So we know now the distance to the Milky Way centers to an accuracy of 50 light years. I mean, that's pretty impressive on a scale of 24,000 light years. So this is really precision measurements we can do with this kind of technique. Now let me say a few more words about Sergei star before I then go and tell you a little more about the sort of cosmology part of this. So Sergei star is this radio source here in the center The radio astronomers can measure its size through what's called very long baseline interferometry, where you take radio telescopes across the entire Earth and then basically interfere the radio light. And when they do this, they find that in the shortest millimeter wavelength, so this is wavelength here, on the vertical axis, its size. Just let's look on the left side here. The shortest wavelength, the size is a mere 50 micro-arc seconds. Now, I already told you on passing that the event horizon of that 4 million solar mass black hole is 10 micro-arc seconds. So this is only a few times bigger than the event horizon. So that strengthens, of course, the interpretation that this must be a black hole and that the radio emission occurs from very close to. And in fact, the radio astronomers next would like to make an image. Because the next thing general relativity predicts is that very close to the black hole, also light will be bent, of course. Okay, so light cannot go straight or will be bent. And in fact, the analysis, if you have a black hole, of light going around the black hole is one that you get in the central region, a dark spot, a shadow, surrounded by a brighter region. If you then add to this relativistic effects, you would expect something like this, sort of an arc-like region, and then the central shadow around the black hole, and then a dim region. This is due to special relativity, and the central part is due to general relativity. And so very, very, very much, I would say, what we know already from the size measurement looks that way. Now we want to have an image. So next year, the radio astronomers will use for the first time a new telescope down in Chile, which is capable of being very, very powerful in millimeter waves, to in fact with other telescopes hopefully make an image here of the radio source. And hopefully when it looks like that, that will be a very powerful confirmation of the black hole hypothesis. Now really very close and showing that photons are bent near the photon orbit around a black hole. Let me skip that one. So finishing this is this particular slide, which is a little technical, so I apologize. So what you see here on the horizontal axis is in logarithmic units, in powers of 10, the size of objects, in units of the size of a black hole event horizon. And then this coordinate is, again, in powers of 10, the density. So normal star clusters, the densest star clusters we know, like globular clusters or the clusters in the centers of galaxies are down here, and a black hole is way up there. So anything here in between is things which you might postulate or you might have a reason to expect. And there are a number of objects which, in fact, scientific colleagues have proposed. You might, as I said before, propose a cluster of neutron stars with a certain density. But then, as I mentioned, this will not have very long to live. In this case, this object here would live only 100,000 years. So it's very, very unlikely to be the solution if you want to have a stable galactic nucleus. It doesn't matter anyhow. The measurements exclude all of this region, which is in gray, okay? And that's what I phrased before. At this point, that this particular object is our best case we have, and there really is not anything plausible anymore which fits into this part, which is not inconsistent with general relativity. Now finally, this year has been another historical year in the sense that one of the other things which Einstein's theory predicted is the fact that the gravitational field can be propagated with waves, very much like the photon field or is electromagnetic field with photons, and that's called gravitational waves. So if you have a black hole and you have a second black hole, which are very close to each other, then they will orbit each other. And as they do so, as you look from a distance, what you see is basically space-time doing this. And that is a distortion of space-time which generates gravitational wave, which will then propagate out at the speed of light. That's the prediction of Einstein's theory. So two black holes which orbit each other start emitting gravitational waves. That means they lose energy. Where does the energy come from? Well, from the gravitational energy of the system, and that means the system's radius will shrink. So it will go ever closer, ever faster. And so this motion of two black holes will very quickly lead to an inspiral of the two black holes. And now comes the critical thing. As the systems approach, any other objects than black holes would merge into sort of a new conglomerate. Take two neutron stars, they would merge into a, basically mal-shaped neutron star system, which would live in this new shape for a while. So that means that the inspiral would then sort of end, but it would still go ahead, and the spiral, the variations of the gravitational waves would go on. Not so with black holes. Einstein's theory tells us that black holes have no hair, right? We have only two numbers to give, mass and spin. And once the two black holes come close enough that the event horizons merge, then you can think of the situation of the astronaut, which is traveling through the event horizon and has no choice but to end up at the center. And that's the two black holes will do in a single dynamical time scale. That at that time takes a fraction of a second. And then all of a sudden, this system like this will beep, boop, and then no more gravitational wave. That's called ring down. So in February this year, our colleagues from the gravitational wave community showed us the first detection of waves from the so-called advanced LIGO interferometer, which has two detectors, one in the southeast of the United States and one in the northwest. And here are the traces of these variations they saw, and I don't want to get into the technical details here, but here you see basically the appearance of what looks like a pretty good detection of these waves. And they look the same at the two sides, here and here, look pretty much the same at the two sides, and there it is. For anyone, even for those like me who are not experts, I tell you, this is one of these moments. That's a black hole. You better learn this. That's a black hole. Why? Because there's a ring down. You see, the train here gets faster and faster. That's the inspiral. And then it stops suddenly within one cycle on both of the observatories. And then there is Funkstille, no more signals coming out. So that means that's where the two systems shed their hair as a double system, and the event horizon started bulging around it, and now you have a black hole system, not anymore of twice the mass. Much of any energy was in fact expended driving these gravitational waves out, but this is a momentous discovery. Of course, it has to be confirmed. A second such event has been seen. We'll have to be cautious, as we scientists ought to be. It would be good to have a second measurement. That is going to be more difficult, because we only have this one antenna. So we should be careful. But it's jubilation, because not only have we confirmed the Einstein's theory, but this is a new tool for astronomy. This is a new tool to basically look into the universe and see with enormous precision the innards of very condensed systems, in particular black holes, as they spiral in, or as systems, stars, spiral into black holes. Extremely exciting. So bolstered with this, we now can plunge on for the last part of the talk and ask the question, all right, let's suppose I'm convinced these black holes exist. Next question you would ask, how common are they? And what is their role in the universe? And so what we can do in this plot is we can go in the local universe, in the universe which you've seen in the movie, and chart out the possible central mass concentrations, for instance in the Andromeda Nebula, or other galaxies which you saw on that trip, and try to measure the central mass and assume it's a black hole, like in the Milky Way here, and plot that as a function of the mass of the system, and there is a moderately good correlation. I don't want to get into the details about the scatter and so forth. The fact that there's a correlation already is astonishing, because the Andromeda Nebula's black hole, like the black hole in our Milky Way, knows nothing about Andromeda. Because the Andromeda knows something about Andromeda, but the Andromeda Nebula doesn't know anything about the black hole. Because the black hole is quiescent, doesn't do anything. And so for the stars out there in the outer parts of Andromeda, they can't tell whether there's a black hole in the center. The gravitational action of that black hole is negligible for those stars, like in our own Milky Way. So how can there be such a correlation? Now the answer might be in the past, when both systems formed, and perhaps then the action of the black hole on the surrounding galaxy was important. And that, in fact, is the last part of the talk, where we now ask the question where this all came from. And that's basically traveling into the past, which we can do in astronomy. Time machines are a tool we use every day. Why can we use time machines? Because the speed of light is finite. And so as we look into the distance, at the same time we look far away and in the past. And our machines we have, for instance with Hubble, in this picture of some part of the sky, we see objects which are objects as they were 10, 11 billion years ago, only 1, 2 billion years after the Big Bang. So we can chart out the history of ourselves in a way, at least statistically, from looking into the past with other objects. And that teaches us that the activity of galaxies in terms of their star formation, galaxy formation, that's the blue curve here, as we basically go back in time or go away from the Big Bang, as we go back in time, increases. The Milky Way now, in this epoch, produces one new star per year, in a system which is 60,000 light years across and has 100 billion stars. That's a feeble attempt of renewing yourself. At the same time, the Milky Way 10 billion years ago, we can now say from many measurements, produced 100 times as many stars per mass of galaxy. And that was because at that time the universe was denser, there was more gas coming into the galaxies, and so star formation was just much more productive. But not only star formation. The red curve here is the activity of the black holes. And as you see, the activity of the black holes also increases by about the same factor here. So the quasars were there, which we see today, they were much, much more active. Okay, and so clearly, at that time, the quasars, or the massive black holes in the galaxies, were producing much more energy. And that, potentially, could have been enough to basically influence the evolution of the galaxies in a negative way, you could say, because they could stop the formation of stars in galaxies and make them basically age very quickly and turn them into passive galaxies. We can do this now with the telescope we have available to times which are only about 6% of the current universe's age, 800 million years ago. There is this light speck here, is a 4 billion solar mass massive black hole, 800 million years after the Big Bang. And so we don't understand how you could do this so close after the Big Bang. That's one of the substantial challenges, how you can grow such massive black holes so early. But the growth thereafter is obviously coupled with the growth of galaxies. And that we can test quantitatively, not only with measurements, but also in supercomputers. So I will show you at the end now a state-of-the-art supercomputer simulation of galaxy formation, which will show you how in a universe like ours, initially galaxies formed in the centers of so-called dark matter concentrations, which dominate the mass. And then inside of these galaxies, ever more grew, and inside of the galaxies then black holes formed, which then started spewing out material through their energy output. So let's have a look at this fantastic motion picture, so to speak, which is of high scientific value. Now you see on the left side in the bottom, that's the time after the Big Bang. So we are now at 1 billion years after the Big Bang. The blue is the dark matter. So that's the, if you like, the potential bathtubs into which baryons, normal material, drop and form new galaxies. And these you can see as red central regions. Over time, we're now 2.5 billion years after the Big Bang. Already pretty big galaxies are now forming at the centers of these dark matter halos. And now you all see thunderstorms of gas being thrown out of these galaxies. There's an explosion. And that's because in the computer, one of the black holes grew up so much in mass during that time that it ejected mass from the galaxy. And all of a sudden you see that this fantastic scenario of exploding galaxies, you could almost say, basically active black holes terminating the accretion activity, or at least limiting it, and thereby controlling the evolution of entire galactic systems through their energy output. This is very much verified, I should say, by the observations which we're doing. So theory and observational work is very much going hand to hand, at least in a fairly plausible, semi-quantitative way. We still have a lot to learn here. We don't know who was first. We don't know which were the first black holes and how massive they were and how they were formed and whether there might have been black holes which already were there in the Big Bang. All of this needs to be explored in the next 10, 20 years. But we've learned that these massive black holes play an enormously important control system, feedback loop control system in the ecosystem of galaxies. And so they're not just randomly there, they are there because they are a major player in galactic cosmological evolution. Finally then, what are we going to do? Well, I've already indicated it to you. We will now go ahead and use the next years, hopefully with luck, to do gravitational experiments on the black hole in the Galactic Center, hopefully showing that GR is correct, perhaps discovering new things with these techniques. Who knows? The sky is the limit, we hope, and it's been a wonderful trip, and I hope you enjoyed it, and thank you for coming.